Never be afraid. There's nothing which is known which can't be understood. And there's nothing which is understood which can't be explained. For over 50 episodes now, my team and I have brought you to the very frontier of knowledge in physics and astronomy. And still, our mission goes on. To present you with your birthright, an understanding of the universe. I've traveled the world seeking out a certain type of genius. Masters of not only their academic disciplines, but also at explaining their research in understandable ways. And I've bestowed upon these women and men the title of Titanium Physicist. You're listening to the Titanium Physicist podcast, and I'm Ben Tippett. And now, allez, physique! One thing I find fascinating is how an assembly of one type of thing can cooperate to unwittingly act like another type of thing. We are not unfamiliar with examples of this. There's something called the zeitgeist, for instance, the literal ghost of an era, where the public mood is palatable and coherent in some kind of weird way. Instead of just millions of disparate opinions, everybody's kind of thinking the same thing. Where does that come from? Like how everybody all of a sudden started growing beards. Where did that come from? Like, in the last 10 years, suddenly everybody's wearing beards. No one in particular told us that beards were cool looking. It's just that everybody kind of changed their minds on the topic all of a sudden. And this type of thing happens a lot in physics. For example, an individual water molecule is just a particle. It bounces off all the particles surrounding it, and that's its life. But if you have enough of these molecules, you get a fluid, a river. Waves travel across the top of it. It flows, it eddies and curls. It sticks to things. It carves canyons. It has all these macroscopic qualities that don't have any apparent cause at the scale of an individual water molecule. Or consider metals. You got individual atoms. Each shares valence electrons with its nearby neighbors to form a rigid structure, and then suddenly at the macroscopic scale, electric currents flow it, just like water through a pipe. What capacity of the individual atoms is it that allows the distinct behaviors to show up at the large scales? Now, you might be unconvinced. You might be like, well, those are both examples of particles acting together to make something that acts like a fluid. Big deal. Crowds of people acts like fluid. Well, there are also examples where the opposite is true, where you got large scales cooperation of tiny little things that generate what we recognize at the large scale to be a particle. And I don't mean atoms in a baseball. I mean, when you study the thing, you say, there's a particle. But then when you look at it, there's no particle in there. It's just macroscopic behavior. We call those quasi-particles. It's absolutely bananas. Anyway, my favorite example is called a phonon, where sound waves traveling through a crystal act just like particles. Anyway, that's today's topic. So, speaking of things that are made of particles, Anthony and Megan Leon are software developers, and they live in Hawaii, and they're also made of particles. Hello, Anthony and Megan.
Hey. Hi.
All right, Anthony. All right, Megan. For you, I've got some magnificent physicists. Arise, Dr. Fiona Burnell.
Boink.
Dr. Fiona did her undergraduate degree at UBC and her PhD at Princeton. She's now faculty in the physics department at the University of Minnesota, where she's a specialist in condensed matter. And arise, Dr. Darren Peets. Dr. Darren did his PhD at UBC and is currently a Cheetah Fellow at Fudan University's Advanced Materials Laboratory in Shanghai, China, where he studies magnetic materials and superconductivity. Okay, everybody, let's talk about phonons.
So, What I love about phonons is that they capture sort of two of the most fundamental aspects of what we have to think about when we study materials, which is they tell us that we need to think about both the interactions between particles in the material, in this case, between the atoms themselves, and we also need to think about quantum mechanics. And in fact, phonons were sort of one of the first examples where people really understood that these were both essential in understanding physics of materials. So back in the late 1800s, one of the few experiments that people could do on crystals at the time was they could measure what's called their heat capacity. So, basically what happens when you heat something up is that you're putting energy into it. And so what they could do is essentially measure how much energy you would need to put into a given material to change its temperature by, say, 1 degree. So this was something that, people could do without the sophisticated laboratory equipment that we have today. So in the late 1800s, before people sort of really understood very much about quantum mechanics, most of the pictures people had in their heads of things were classical. And these classical models of the heat capacity of a crystal, which we'll talk about in a moment, basically predict that the heat capacity should be essentially independent of temperature. And what happened was that as people started to be able to do these experiments at lower temperatures, they were able to notice that that was in fact not true in real solids.
Okay, so before we go any further, Megan and Anthony, are you familiar with the heat capacity as a physical thingy?
Not really, no.
Oh, okay, so the moral of the story is different materials require different amounts of energy to heat them up by 1 degree. So some things like aluminum heat up with very little energy, right? It doesn't take much heat to get your piece of aluminum to room temperature. And other things take a ton, like water is notorious for having a huge heat capacity. There's two ways to think about it. It either takes an enormous amount of energy to heat water up 1 degree, or alternatively, if you heat water up to a certain temperature, it has tons of energy, and so its temperature will come back to room temperature very, very slowly because so much energy is stored in that.
Oh, okay. Yeah, that makes sense.
So what they were doing is they were taking crystals and they were like, what do we know about crystals? I don't know. Let's make models of it. And their conclusions, based only on classical physics and what they knew about thermodynamics at the time, suggested that the heat capacity would be constant, that it wouldn't depend on temperature. And what Fiona said was, as they did experiments on crystals, on metals, they found that the lower the temperature got, the less heat capacity the system had.
Okay.
So the question was, why does it act like that? Why does it act in this particular way?
Right.
And this was turn of the century problem, right? 1907, Einstein put his 2 cents in, that type of era, right? So right on the cusp of people needing to insert quantum mechanics and the idea of quantum mechanics into their experimental physics.
Okay.
So heat capacity it's an interesting thing because it's kind of like asking somebody, well, let's say there's a person with pockets, and you're going to hand him oranges, and he puts 1 orange into each pocket, and you're asking, how many oranges do I have to give him before the number of oranges in his hand increases by 1? So different people have different numbers of pockets. I've got 4 pockets, which means that you have to give me 5 oranges before I have to store 1 in my hand, right?
Right.
You have 8 pockets, and so somebody has to give you 9 oranges before you have to store 1 in your hand. You dig?
Yeah.
So particles are kind of like that. A particle can store energy in a variety of different ways.
Your oranges are heat in this case, by the way.
Yeah. To give the end of my awesome analogy away, the oranges are heat in this case. So a particle can store heat energy in a variety of ways. You can cause it to vibrate left or right. You can cause it to spin a little bit faster. You can cause it to bounce back and forth, or you can cause it to bounce up and down.
Right.
So the different ways. So the deal is that if you give a particle a little pack of energy, it will store it in one of those ways. And overall, each time you give it another little packet of energy, it's going to store it in another way until, overall it has to bounce back and forth a little bit faster. And so the moral of the story is, depending on, we call these degrees of freedom. It can vibrate up and down, or left or right, or back and forward, or you wiggle in some certain way. And so if you're dealing with a molecule, the more degrees of freedom it has, the more different ways it can store energy, and the more energy it's going to take to increase the temperature of the material. because it can hide a little bit of energy in vibrational energy, and it can hide a little bit more energy in spinning energy, and it doesn't have to devote that energy into vibrating around temperature energy. Does that make sense?
Yeah.
So the question is, where's the energy going? How is the system storing energy? In what way is it storing energy so that you get this particular type of heat capacity, this particular temperature dependence in the heat capacity?
So there's multiple ways for the molecule to store energy, and then once you have achieved all of those ways, like you've stored energy in all of those different ways, then it increases its temperature.
Yeah, by a little bit, right?
By a little bit.
Yeah.
What is the temperature in that analogy? Like,
the temperature is when the particle bounces back and forth against other things.
Oh, okay. Okay, I get it.
So it won't manifest as a temperature difference until the energy you give it makes it bounce back and forth. And so it's kind of like the difference between, if you take a basketball and you throw it against a wall, the basketball is a very simple object. In a basketball, most of the energy you give it in throwing into it will manifest as motional energy. Whereas if you take a lamp, like one of those IKEA lamps that's covered in springs, and you throw it against the wall, some of the energy, when it hits the wall, will bounce back and you'll get it moving again, but a lot of the energy will be dissipated into causing the lamp to vibrate and deform itself and stuff like that.
In both cases where it's actually in contact with the wall, it's deformed.
Yes, that's right. At that moment.
In one case, you get the original form back when you're done.
Yeah, because it's a simple system, and there's not very many different ways it can hold the energy internally, right? And so the complexity of the system and how it can store energy internally determines how much heat capacity there is in the system. Does that make sense?
Yeah, it does. So what makes a water molecule so complicated so that it has such a high degree of this?
The hydrogens are actually shared between two adjacent oxygens, and then they choose one to be closer to at any given time, so they can move back and forth. But of course, if one moves away, then one of the other ones has to move toward that oxygen, so there's always two that are close.
Oh, okay.
Okay.
You also have the ability for the thing to flap its wings, basically. Like this angle is supposed to be 104 degrees or whatever, but it doesn't have to be exactly that all the time. It can vibrate a bit.
The wings in this case are the hydrogen atoms bonded to the oxygen one. So it can, it's just super jiggly.
Okay.
All right. So Fiona, where were we?
I think the basic overview, and maybe we'll talk about the different models in detail, is that so people were thinking about the heat capacity of crystals, and as Ben was explaining, basically in order to understand heat capacity, you have to think about what, if you like, sort of particles or modes, or what's going on to kind of store the energy in the system. And the earliest model of this was due to Boltzmann in the 1890s, and he sort of said, you think about the atoms in your crystal as being sort of balls, if you like, attached with springs, and you really think about, just balls and springs in a kind of classical sense, you get the correct answer at high temperature, but in fact, something which was very clearly not consistent with experiments as they got to lower temperatures. So there were a couple of modifications of this. Basically, Einstein was the first person to introduce quantum mechanics into the theory of vibrations of atoms and solids. And he had a model which sort of qualitatively, in some sense, got the right behavior at low temperature, but it was wrong, in a sense, in a quantitative way, depending on what you mean by quantitative or qualitative. I mean, he predicted the wrong mathematical function for how it behaves with temperature, but he did.
It was like the wrong math, but it got it right in the solution.
Well, what his model got right is the fact that if you look at this heat capacity, it basically goes to zero for most solids as you decrease the temperature. But he actually had the wrong prediction for how it gets there. So he had quantum mechanics, but in fact, he didn't include any interactions between the atoms. And then the third kind of modification was due to Debye, who introduced, as well as quantum mechanics, included interactions between the atoms in the crystal. And when you do that, you get essentially a very good fit to the experimental data. So that's kind of I guess if you like, it's a historical picture, but this was, really one of the first indications that quantum mechanics it was a fundamental part of understanding elementary properties of solids, like how they absorb energy, essentially.
So the heat capacity, you were saying, like, it goes down the less energy you give it?
When you cool it.
Okay, so at lower temperatures, as Ben was saying, there's, if you put energy into any system, there's a number of different sort of ways that the energy can be stored. Imagine just a room full of bouncy balls. So that's kind of like a gas. So can you put some energy into that? And basically what's happening is, it's going to be kind of random. So some of the balls are moving very fast. Some of them are moving slowly. And basically at lower temperature, there are going to be a lot less balls that are moving very quickly. And so what that corresponds to in terms of thinking about kind of modes at different energies is it means that you can have, a molecule that has different modes. Maybe it has vibrational modes and rotational modes. And or if you think about these atoms that are coupled in the solids, some of the, modes have higher energy than others. And so basically what happens is that as the temperature goes down, you have a lot less of those high energy modes going on and a lot more of the low energy ones. It turns out that means that, basically as you go towards zero temperature, the energy starts to be, more and more independent of temperature.
Okay.
If you're trying to store energy in the system, at low temperatures, a lot of the places where you would try to store energy just aren't available. You would require too much energy to actually put something in there, and at low temperatures, you don't have that. Everything's cold.
Okay, so in the classical sense, they were thinking no matter how low you got the temperature, the heat capacity would be the same. But it turns out it's not because there's less place to put the energy.
Correct, yeah. So it's sort of a quantum mechanical effect.
Oh, that's interesting.
Yeah.
It's like you've got the coat pocket analogy where there's a person you're giving oranges to. The colder they get, the more pockets they zip shut. And then so the amount of energy it takes to change the temperature changes.
Okay.
Does that make sense?
So like the heat capacity goes down to zero the closer you get to, I would assume, like absolute zero. And so the amount of energy you have to put into the solid is very low in order to get it to increase by 1 degree. And then it just continues to increase as you increase the temperature.
Yeah, because as it warms up,
and there's more places, there's more pockets.
Yeah, it releases more internal ways the system can hold energy.
Oh, okay. Cool.
So before we start talking about phonons specifically, what they are, let's start talking about these different solutions.
Your solid, you've got all of these atoms. They're in some sort of set arrangement in space. So the first thing to think about, the simplest model would be each atom is a ball, and then they have interactions with the atoms around them, so those are springs. So if I have these atoms on some sort of a grid in 3 dimensions, and I say, okay, all of these are fixed in position, and then I look at one somewhere in the middle, well, I can move it up and down, or left and right, or toward me and away from me. And if I take it out of the center position, it's going to have one spring pushing and one spring pulling to bring it back to the center. And I can give it a kick. I kick it to the left and it moves to the right and it bounces back and forth for a while. I can have the thing vibrate up and down toward me or away from me, or I can do something that's a combination of them, like I can pull it diagonally and it'll run around and back and forth diagonally. So those are the basic modes that are available for it on that one site. But the other things are not fixed. They can vibrate as well. So what ends up happening, you can imagine I take this atom and I push it, and I really push it away from myself kind of hard, and everything around it goes with it. And so this travels, and this is essentially a sound wave. And if I wiggle it left and right, everything will wiggle left and right as well. And this actually looks more like light. It travels away from me, but the displacements, the way that things are moving, are not away from me. They're just left and right. And I can do that up and down as well. So the one where I push it is called an acoustic mode because it's similar to sound. The one where I wiggle it left or right, up or down, those are optical modes, and there's 2 of them. And this is a collective wave thing in the crystal.
So up and down and left and right are optical, and pushing toward or away from you is acoustic. Like a sound, acoustic. Yeah. Why are those differentiated?
So photons, light, only have 2 of the 3, for instance. But phonons have all 3. The only real difference is that the direction that it's traveling is the same direction as the way the things are moving individually. It does make a difference in what the energy is as a function of the momentum of the material, or the momentum of this wave.
Okay.
I think one of the reasons for the nomenclature is, so basically the acoustic modes are ones that, basically as the wave moves slowly, it carries very little energy. So this kind of relationship between the speed and the energy is what you would expect for water or something like that, an ordinary wave, and that, that relationship actually defines how quickly sound propagates in your solid and stuff like that. The optical modes, one of the reasons that they're called optical modes is if you actually shine like a laser or something onto your system, and your system absorbs photons from that laser, the photons can excite these optical modes sometimes, but they can never excite the acoustic mode.
Oh, that's interesting. So why is it that a photon wouldn't be able to push the system in a particular way?
It has to do with the energy. So it has to do with the relationship between the energy of the photon and its momentum. So when the photon comes in, it transfers both energy and some momentum. And basically, a photon of a given momentum always transfers a relatively large amount of energy. So you can have a phonon which has a small momentum and like a very small energy. But basically the photon, as soon as it has a momentum that's not tiny, has, basically because the speed of light is so big, is going to transfer a significant amount of energy. And so that's why it can't access these modes which have very low energy when they're low momentum.
Oh, okay. So it just doesn't interact because they don't accept that type of energy, that high amount of energy.
Yeah, exactly. Yeah, it would have to. Yeah, that's right.
So have we defined what a phonon is?
So we've got a wave traveling through the material, and we've got 3 different types of waves that can travel through the material, 2 types that are optical and one that's acoustic.
Right.
Well, if you have a wave, you can also have a particle. Because it's a wave, it's a particle. This is what quantum mechanics will tell you.
Wave-particle duality.
Right. You said that sort of like axiomatically, like it's that if there's a wave, there can be a particle. But like in the ocean, like there's a big wave there, but you don't normally see an ocean particle like spring out of that. So like what is a phonon in that context? How do we represent it as a particle?
So I think it's helpful to be precise about what you want to mean by a particle. So when we say particle, I think that invokes this idea of something like an electron
like or something. Yeah, like a ball or an electron or just something. Yeah.
Yeah, like something that you can microscopically kind of look at and say, oh, it's this point thing at all. No matter what scale you look at, basically, it's a point object. And so one of the things that Ben touched on in his introduction is that when we study materials, there are sort of particles, and then there are what we often call quasi-particles, which are things which behave like particles in the sense that they have a well-defined, energy and velocity. And I mean, they can scatter off each other, but, basically they're well-defined excitations for long periods of time. And so if you think about your model of balls and springs, or like my favorite image to have in my head is imagine that you have a slinky or a string or something like that, and you start shaking your slinky, right? And so you know that if you push the slinky, you see this wave go traveling down it. And that wave is carrying a fixed amount of energy, and it's traveling at a particular speed. It has some shape that, kind of propagates along. And the shape doesn't really change as it moves. So that wave is really what we mean when we say, a quasi-particle. That wave is your classical analog of a phonon propagating along, carrying some energy.
Oh, okay. So it's like the representation of the wave, like the aspects of the wave that are going through the slinky.
Like the effects, but it's not an actual particle. Like it has a real effect, but it's not real.
It's not like an electron.
If you zoomed in, you would just see slinky everywhere. Microscopically, the slinky is all made of slinky, but there is this excitation. You put in some energy and it propagates at a speed.
Okay.
So that's, I think, the right image to have in your mind when you want to think about a phonon as a particle.
Not be convincing to you that phonons are particles at this point of the game, because you're like, well, yeah, then isn't anything a particle? And you're like, so before we go on, let's go back to that heat capacity thing. Not because it's particularly useful in talking about phonons or imagining what they are, but because, for me, it kind of put the stamp particle on the thing. So earlier when we were talking about heat capacity, we were saying the issue here is, where is the energy stored? How is the energy stored? Can we name all the different ways the energy is stored in a system, right?
Right.
So Darren was saying, when you describe a crystal as a bunch of particles that are kind of locked into fixed places in a lattice, where there's an atom at the center, and he has an atom above him and an atom below him and an atom to each side, and he's kind of pushing on them, and they're kind of holding him in place. I guess it's a he now.
Yeah.
The earliest methods for describing how energy was stored in the system imagined each individual atom as being held in place by the ones around it. Okay? They say, where's the energy stored? Well, the energy is stored in the atom wiggling back and forth in place.
Yep.
And so it's like they can wiggle a lot, or it can wiggle a little bit, and it can wiggle in 3 dimensions. It can go up, down, side to side, etc., right? And the problem with that model, as they said, is it doesn't correctly predict, as the temperature decreases, how it's going to change what the heat capacity is.
So basically, the kind of cartoon picture that we have in our mind of a solid is, I take a bunch of beads, I bind them together with springs, okay, and I have this bead spring thing. It kind of looks like a big trampoline. So, if you built this in your basement, this would be a classical system. Obviously, it's big enough for you to touch. Quantum mechanics is not important. And that was kind of the first model this was the Boltzmann model of solids, the first model that people had. And so, you would look at your network, which, I guess trampoline is 2-dimensional, so maybe you build a 3-dimensional one, right? And you basically say, okay, how many, ways can each atom wiggle? And the answer is, it basically has 3 directions it can wiggle in. And so that basically corresponds to that constant heat capacity with temperature. Now, the reason that that's not correct is when you actually think about these phonons, which are kind of the particles carrying the energy. In that treatment, those phonons are classical particles. And in reality, in a solid, phonons are actually, quantum mechanical particles. And that actually affects, if you like, how many places there are to put the energy as the temperature goes down.
So the idea is that how are we going to store the energy? So Einstein comes along, and Einstein goes, the problem with this model, the reason it's not doing it correctly is because we're not quantizing how these particles are wiggling back and forth in place. Okay? So he's like, okay, I'm going to apply quantum mechanics to each individual particle. So each particle kind of has a center location where it's supposed to live, and it's going to vibrate back and forth. But instead of vibrating back and forth classically, it's going to vibrate back and forth quantum mechanically. And that's going to affect how the system stores energy. You dig? So it was wrong, because he wasn't taking into account how if one particle moves a little bit to the right, it's going to push on its neighbor, right?
Right.
And so you can have systems where all of them are moving to the right, or you can have waves moving through the system. And so Debye, what his insight is, so the question is, how do we model the system? Where is the energy being stored? Debye said, instead of individual atoms wiggling back and forth, we're going to treat this crystal like it's a box. And this box is holding a whole bunch of pseudoparticles, but particles, little bosons, phonons, actually, right? And so you say, hey, what are the statistical mechanical properties? How does a box full of these little phonon particles hold energy?
Well, wait, Ben, sorry, I need to say one thing, which is that, so in the Einstein model, there's still bosons, but they weren't, the excitations of each atom are still bosons in the Einstein model, but these bosons were not interacting with each other. And then in the Debye model, he treated them quantum mechanically, they were bosons, but they were also interacting. The model that Einstein quantized would be the equivalent of basically modeling your solid as a large egg carton, and you put like a little bead in each egg cup, okay? And then that bead can vibrate around in its own little egg cup, but its vibrations are not in any way correlated with the vibrations of the beads in the surrounding egg cups. So even that model, when you introduce quantum mechanics, is not too bad. But Debye's model actually basically, more or less quantized this model of beads attached by springs.
So he got rid of the egg cup walls?
Yeah, he replaced the cusps in the egg carton by springs. And the difference is that if you have a bead in its own little kind of dip, it just does its own thing. You put some energy in and it bounces around in its own egg cup. Whereas if you replace those cups with springs, then if you put some energy in, a bead moves relative to its neighbor, right? And so, for example, if I take my egg carton model and I put some energy in one particular cup, so I take a ball in one of the cups and I give it a push and it starts moving, that energy is not going to go anywhere, right? It's just that ball is moving, but it doesn't talk to any of its neighbors. So they're all just doing whatever they were before. Whereas when the beads are connected by springs, then if I push one bead, right, then it's like kind of if you tap on the surface of a trampoline or something, you're going to see this energy propagate through the system.
Okay.
Mm-hmm.
Does that make sense?
Yeah.
Yeah.
So, moral of the story is when we quantize the sound waves, essentially, the waves through the system, the up and down waves when one object pushes on another and you get waves moving through the system, once you quantize those and treat the system as a whole as one that can store energy in those waves, you can properly account for how the heat capacity depends on temperature. So the moral of the story is you have to treat the assembly of waves that are moving through your crystal as particles in themselves, pseudoparticles.
As quantum mechanical particles, right? Not just, yeah.
So as quantum mechanical particles, and in doing so, you end up with the proper relationship. So the moral of the story is, yeah, mathematically you have to say, hey, these vibrations aren't just us speaking rhetorically and saying, hey, it's like the way a wave is a particle, or a tornado, or a horse is a particle. It's us saying, you have to treat these waves as individual particles inside the system, or you don't get the proper theoretical result, matching the experiment. So in some mathematical but very real sense, phonons are particles.
Yeah.
Okay, yeah. So what is it that you're doing when you say we're going to treat them as quantum mechanical particles? Like what quantum mechanical property is it that you're ascribing to them that sort of changes it from no longer being classically tied together with balls and springs, but instead they're acting as one? But what is it about the system that is quantum?
So basically, when we think about particles, we have this idea of, like maybe billiard balls on a table or something like that, right? Where even if all of my billiard balls had the same number, right, there would still be a real sense in which, I could say, well, this particular billiard ball is here and that other billiard ball is over there. And it turns out that quantum mechanical particles don't behave that way. So basically, when particles are quantum mechanical, there's no way that you can tell, if you have two particles and they're at positions A and B, there's no sense in which particle 1 is at position A and particle 2 is at position B, because that's completely equivalent to having particle 2 at position A and particle 1 at position B.
So are they both at A and B?
Yeah, so basically, in a sense, you should think of both particles as simultaneously being at both locations. And in other words, the particles are what we call indistinguishable. So there's just no sense in saying this is particle number 1, particle number 2, and they're really different.
And we're referring to the phonons here, like the particleization of the wave of the movement of the actual particles in the crystal lattice?
That's right. So yeah, in this case, those are the particles that we have in mind, although this statement about indistinguishability is a very general property of any particle at the quantum mechanical level. But it turns out that the fact that they're indistinguishable has a big impact on basically the number of particles that are going to have a given energy at a given temperature. The fact that they're indistinguishable, which is a property of quantum mechanical particles, is what makes the heat capacity different at low temperatures from what the classical model predicts.
Okay. I'm not sure I understand how decreasing the temperature of, let's say it's like a crystal, and then you add energy to it, and now we have a heat capacity. Let's say it's really, really low because we have the temperature that's really low for the crystal. I'm not sure how, the phonons are applying to this situation. How is it that because of that property, because of their quantum mechanical property, I can put just a little bit amount of energy in there to get 1 degree difference? Whereas if there was a higher temperature for the crystal, then I would need to put more energy in. I'm not sure I understand the connection between how the phonons being quantized means that effect is a reality.
Okay, so Electrons are similar. Like, you can't say this electron over here is blue and that one is red. An electron's an electron. And the difference between electrons and things like phonons, when you swap two electrons, you get an overall minus sign in the equations. When you swap two phonons or any other boson, like light, you don't get a minus sign, you get a plus sign. And one consequence of this is that multiple bosons can occupy the same energy level, but that's not true of electrons. Every electron in the system has to have a completely separate set of quantum numbers describing what it's doing.
Is that like the Pauli exclusion principle?
Exactly.
Is that what it is? Okay.
So that applies to electrons and anything with half-integer spin, but a phonon has no spin angular momentum. It's just a bunch of stuff moving around.
Right.
So phonons, light, or other particles that don't have overall spin, like a helium-4, for instance, they behave this way. And so you can get into cases where you've got a whole bunch of them in the lowest energy level, and so you can excite from the lowest to the highest, and you've got a whole pile of stuff there. Whereas with electrons, you've filled them up to some specific energy level, and you're always dealing with what's happening around where you finished filling them up.
Okay, so like when you decrease the temperature of the crystal lattice, then when you add energy to the system, then there's just more.
The phonons keep falling down in energy,
right?
Into the
and so
lowest levels.
There's a ton of phonons down there, and then when you excite them, then it's easier for it to increase the temperature because it's easier to propagate through the system.
In the case of phonons, they can also just go away. But in the case of electrons, they can't go to lower energy levels because there's something there already. In the case of phonons, they can. So you're working with the levels that are at lowest energy. And if there's types of phonons that only exist at higher energy, you just don't have any of those anymore at low temperatures.
Okay.
So optical phonons, for instance, are generally higher energy. When you go to lower temperature, you don't have any phonons of that type anymore. Your energy is stored in the low energy modes because everything can move down into the low energy states.
I want to imagine this like a big block of Jell-O that's jiggling, okay? So imagine you got a cube of Jell-O. The optical modes are the kind of transverse waves, so they're the ripples that move across it. Whereas
it's you putting your finger on the surface and moving it left and right.
Yeah, whereas the
acoustic is you giving it a flick.
Acoustic ones are compression waves, so it's getting bigger and smaller. It's squishing, right? And you're saying that the left and right wiggling modes are higher energy. And so there's some statistics to how the system evolves as we extract energy from it, where the side-to-side wiggles go away first, and then eventually the compression waves get smaller and smaller and smaller until they all go away.
And so if you put energy into the crystal, you don't have access to those particular types of jiggles, the optical jiggles, until you get to a certain energy?
At higher temperature, you can access higher energy modes.
And then that crystal has the capacity to basically store the energy in that additional way so that heat capacity increases.
Right. But if it's cold, those aren't available.
I'm glad I introduced Jell-O.
Well, there's always room for Jell-O.
Let's move on to other applications and stuff.
Well, I think we should say a little bit about Rowland superconductivity, which is one of their most exciting kind of consequences, if you will.
So in a superconductor, what's carrying electrical current is pairs of electrons. But the electrons, they don't like each other, they repel each other, so something has to stick them together into a pair. And in conventional superconductors, that's a phonon. And the way that you can sort of see that this is connected with the lattice is the simple picture is if you have an electron moving through, it's negative. The nucleus of the atom is positive. They want to move toward it a little bit. So you actually have this motion of the nuclei of the atoms toward the electron. The electron zips away somewhere, and then some other electron sees this concentration of positive charge because the nuclei moved toward this place where the other electron was. So the second electron is attracted to the fact that the first electron was there. That's the very simple cartoonish picture, but it's a coupling between the electrons and the lattice that's doing this. And this seems to be how the conventional superconductors pair their electrons. It's not the case for the high-temperature cuprate superconductors and a few types of low-temperature ones, and the jury's out on a couple of other classes.
When you say high temperatures, how high is that going now?
High-temperature superconductors are liquid nitrogen temperature, roughly, so the transitions are 40 Kelvin up to about 140.
Oh, cool.
Okay.
For a low-temperature physicist, it's really, really hot.
Right.
It's at the point where you could call it room temperature superconductivity if you got a very, very cold room.
So I was just trying to visualize what you were saying, like why the two electrons were paired. I'm not sure. Where did the first electron go? Like it left, and then the other one was like, oh, there's a space there where it's positively charged, so it goes towards it. But where did the first one go? Like why did it leave in the first place?
I think maybe one thing that could be said here is that in general, if you think about an atom, you think about, the atom has some electrons, and, if you just have the atom in a vacuum, the electrons are bound close to the nucleus of the atom. In a metal, however, in fact, some of the electrons are kind of stuck near their nuclei, but the electrons that actually conduct electricity, basically, they're not committed to being close to any particular nucleus. So in general, they're kind of moving around in the crystal at all times. So your kind of expectation for an electron is that it is going to be itinerant. And so basically, it's here now, and it causes this positive charge locally, and then it leaves because it was on its way somewhere anyway. And then another electron feels that positive charge, and maybe it deviates from its previous trajectory a little bit to visit this positively charged region.
And those two are paired together because they're like following each other, bouncing between these positive charges.
Yeah, essentially. Basically, what has to happen is that the energy of this kind of staying in each other's periphery to benefit from this charge cloud has to be bigger than the kind of random. This is kind of a approximate picture, but you can imagine these electrons having some random energy as they move around. But basically, if you get cold enough, then this is the glue that binds this pair of electrons together.
Megan and Anthony, do you remember your basics about superconductivity?
We just listened to it.
No resistivity when when the electrons are going through the superconductor.
Uh-huh. Do you remember about Cooper pairs?
No.
So the particle that's actually transmitting the current is a combination of two electrons and at least part of a phonon.
So to bring it back to what we were talking about before, you know how Darren was like, there are these bosons and then there are these electrons. So phonons are an example of bosons. And he was talking about the statistics of what happens, how an electron will behave differently than a phonon will when you cool it down.
Right, because it can't go to a lower state of energy because there's something already there.
That's
Since
right.
It can occupy the same quantum state, then it can't be in that space, so it has to stay in the upper energy level.
Perfect. Yeah, exactly. So the difference between those two different types of particles, one of them are called fermions and the other are called bosons. Electrons are fermions and phonons are an example of a boson, is that one of them has 1/2 integer spin, so the spin of an electron is 1/2, and that means that it has to obey the Pauli exclusion principle, and a phonon has spin 0, or things that have spin 0 or spin 1, those are bosons, and they don't, and they can all go to the lowest energy level. So what happens inside of a superconductor is that all of the
Two
electrons...
halves make a whole.
Yeah, all the electrons in it combine. So they kind of get partnered up. And when they partnered up, then combined, they have an integer spin, and they start acting like bosons. And so even though on their own each electron will stack up in that way you were describing because of Pauli, once they combine up, you can bring those pairs all down to the lowest energy level.
Yeah, that makes sense.
And then when they do, they all act exactly the same way, and you get this large-scale superconductivity property. And so what Darren's saying is, the question here is how the two electrons pair up. When they pair up, it's called a Cooper pair. And what he's saying is they pair up because a phonon sticks them together.
Oh, okay.
So we were describing what a phonon is earlier, and it was sort of like this representation. It was like a wave, but going through a physical system. What is it in this context? What is a phonon between the two electrons?
The phonon is basically describing a wave in which, so if you think about, the wave in the slinky.
Yeah.
Right.
You can think of, for example, a compression And so that's going to bring, if you put beads at fixed distances apart on the slinky, then as your wave comes through, some of those beads are actually going to be closer together. And then, some of them are going to be farther apart. So the phonon is always describing that process in which the distance between two adjacent atoms gets, either compressed or expanded. So basically the reason that this couples two electrons is that, an electron has a negative charge. So if you have an electron that's sort of hanging out, for example, between two atoms on a lattice, then that's going to actually pull those two atoms in towards it. So basically that pulling motion, if you like, is kind of exciting a phonon.
Okay.
The phonon exists over the entire material, and so do the electrons. So we can sort of justify it very locally at one site, but overall, the electrons and the phonon, their waves, they're covering the whole material.
Okay.
So they're doing this over some spacing. You can imagine this happening at one location in space, but it's also happening in a bunch of others at the same time.
Because it's all the same thing at that point, like it's a quantum system.
The electrons are spread out over everything.
Right.
As are the phonons.
But with superconductors, like the way that I understood it from when we listened to the other episode, the electrons were moving. So, they're everywhere, but they're also moving, right? Like they're, okay.
They're a wave and they have momentum in that wave.
Darren, do we want to go through all these other examples of uses?
We mentioned that the acoustic phonons kind of look like sound waves. They do actually carry sound. So if you're moving sound through a solid, it's traveling in phonons.
Oh, that's cool.
And we mentioned heat capacity. You're storing heat in these materials in the phonons. So heat is traveling through the material as phonons. And it turns out one of the big limiting factors in making computer chips, particularly processors, is the ability to get heat out. So if you really want to get heat out as effectively as possible, phonons are actually something you need to think about, because that's how you're doing it.
Huh.
So I think that tends to be the higher energy phonons. The lower energy ones are probably kind of saturated by room temperature. But they need to think about parts of the phonon spectrum for the material they're working with and how they can best get heat out of the material.
That's cool. Yeah.
I guess one other thing that we could mention is there's some types of structural phase transition where if we had balls on springs where everything's in a nice cubic grid, there's some types of materials where at low temperature it turns into something else where, maybe the balls want to pair up in a specific way or something. And the way a few types of this transition work is, so you've got some central ball and it's got its arms out. And it's got a phonon where one arm is out to the left while the other one is in to the right. And then it switches so that the right arm is out and the left arm is in. And it's just sort of going back and forth, punching the air in both directions.
Right.
But, maybe this phonon mode actually freezes out at some temperature and this thing is stuck with its right arm out. And so this has happened throughout the crystal. And you've basically gone through a structural transition and now everything's in a pair because it's holding the thing on its left much closer.
So that actually effectively changes the structure of the crystal because it changes the location where the atoms kind of spend most of their time.
So they get stuck there, and then does it only change the structure of the crystal at that temperature? And then when you increase the temperature by increasing the energy, then the structure changes back to how it was?
Yeah, it can melt. Yeah.
Well, that was fantastic. Okay, so thank you, Fiona. Thank you, Darren. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. Here is some fruit. Fiona, you get a coconut. Good. And Darren, you get a kiwi. All right, I'd like to thank my guests, Anthony and Megan Leon. Thank you very much, Anthony and Megan, for coming on the show.
Thank you.
Thank you. This was awesome.
All right. Hi, everyone. Well, that was the first episode of Season 6. I've lined up a whole year's worth of fantastic episodes for us to record, and I can't wait. All right, so it's announcement time. First, please give us an iTunes review and tell other people about us online. Why? Because people keep their deep love of physics secret. They want to know that there's a show like ours online, but they don't know that we exist. A subset of your friends and family will be really happy to hear about us, and the rest of them, well, I'm sure they'll endure you talking about a physics podcast you like because they love you. On another note, We're still humbly soliciting your donations. Your donations go to paying the server fees and our project to transcribe the episodes as they come out. That's right. You heard right. Thanks to your support, we've transcribed our entire back catalog. And I'm pleased to announce our newest project, which is to buy decent microphones for all of our regular titanium physicists. You can send one-time donations through PayPal off our website, or you can go to our sweet Patreon site and give a recurring $2 donation or whatever. Speaking of which, this particular episode of the Titanium Physicists has been sponsored by a collection of very generous people. I'd like to thank the generosity of Weena Brett, Elizabeth Hargrave, and Jordan Young for their donations. And I'd also like to thank Keegan Iad, Adrian Schoening, Adrian Bastias, Cadby, Joe Campbell, Alexandra Zani, Weena Brett, Eric Deutsch, Etienne Raymond, and a gentleman named Peter. Mr. Gareth Easton, Joe Piston, David Johnson, and Anthony Leon, as well as Doug B., Julia, Noah Robertson, Ian, and Stu. Mr. Frank, Philip from Austria, and Noisy Mime. Mr. Shlomo Dalal, Melissa Burke, Yassine Ouarzazi, Spider Rogue, Insanity Orbits, Robin Johnson, Madame Sandra Johnson, Mr. Jacob Wick, Mr. John Keys, and Mr. Victor C., Ryan Kloss, Peter Klipsham, Mr. Robert Halpin, Elizabeth Teresa, and Paul Carr, Mr. Ryan Newell, Mr. Adam K., Thomas Shai Ray, Mr. Jacob S., a gentleman named Brett Evans, a lady named Jill, a gentleman named Greg, thanks Steve, Mr. James Clausen, Mr. Devin North, a gentleman named Scott, Ed Lowlington, Kelly Wienersmith, Jocelyn Reed, Mr. S. Hatcher, Mr. Rob Abrazado, and Mr. Robert Stietka. So that's it for Ti-Fi this time. Remember that if you like listening to scientists talk about science in their own words, there are lots of other lovely shows on the Braculo Media Network. The intro song to our show is by Ted Leo and the Pharmacists, and the end song is by John Vanderslice. Good day, my friends, and until next time, remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hop down Magnolia Boulevard. No way he'll survive.
So Megan was saying she was reading a little bit about phonons a few days ago, and she said that somebody was making like some sort of singularity or a black hole out of phonons.
Oh, yeah. That's right.
I was wondering if you guys had ever read anything about that.
Oh, Ben should answer that because that's Bill Unruh's thing, right?
Yeah, it was
Okay,
a
here, hold
Canadian who designed it, I think, but I can't remember who actually did it.
I think he calls it the dumb hole. I might be thinking about the wrong thing, but I actually saw him give this this talk once where he was explaining black holes, and he had this picture. I actually really love this picture. The picture involves, so you have a river, and the water is moving at some speed, and there are fish in the river, okay,
Right.
And there's there's a waterfall, okay. But okay, so the fish are in the river and they're trying to swim upstream, but the current is moving faster than they're swimming. And then you imagine a scenario where, the fish, so they're getting frustrated, obviously, they're not getting up the river, and so they start to scream. Okay, so they're screaming, and that's creating this sound wave that's, propagating forward from the mouth of the fish. And so the question is, what is a black hole? Well, a black hole is like the scenario where the water is moving so fast that, the fish screams and you have this sound wave coming out of the fish's mouth. But the current is so fast that sound wave is also propagating downstream. So like a fish, or, if you put a microphone upstream, once your fish has gone past that microphone and it screams, you're never going to hear, You're never going to hear the fish scream because everything is basically moving downstream so fast.
If the fish is screaming upstream and the microphone is downstream, you'll hear it. But once you get past the microphone, then you won't hear it because the stream is carrying the wave faster than it can propagate through the water.
And that's a little bit like the situation in a black hole, where if you fall inside the black hole and you try to shine light out, you have a friend who's outside the black hole and you want to signal an SOS with your flashlight, but that light is never going to make it to your friend because your friend is on the other side of the horizon and the light will never get out of the horizon.
Yes.
And so we've done something similar with phonons.
Okay. Yeah.
People actually made it?
Yeah. Okay, so
cool.
what you're talking about, you called it a dumb hole, right?
I thought that was because it was Bill Unruh's thing. I'm pretty sure.
That's the name of the model. So Bill Unruh, it started out as an analogy that he would use to explain black holes to lay people, which is just this kind of fish thing. So it's like, hey, once the fish is over the horizon, once it's far enough down the waterfall, it can't talk to anybody because the water's moving faster down than the sound waves can move up. Right? Which is what you just said, Fiona. So it turns out that it's a little bit more than that. That the analogy is actually really incisive. You can build mathematical analogs for how black holes work using sound waves. So you don't necessarily need to make a waterfall because the rate that sound passes through the water depends on things like the flow rate and its temperature and how tall it is and all sorts of things. So you can build in a laboratory other systems that are mathematically analogous to black holes. So you can build these sonic black holes where water is flowing through the system in a way that waves travel through this system in the same way, analogously, that they might evolve in and around a black hole. And what this lets you do is it lets you test all sorts of predictions that people have made about black holes. Stephen Hawking made a prediction that said black holes emit a certain radiation. And so what this has let people do is it lets them test to see if in this mathematical analog, in this sonic black hole, the mathematical equivalent to that Hawking radiation actually gets generated. And they've detected it. And it's actually a really interesting thing.
That's really cool.
Anyway, moral of the story is...
They detected acoustic Hawking radiation?
That's right. They detected acoustic Hawking radiation.
That's awesome.
Which is awesome.
A lot simpler than testing a real black hole.
Yeah.